Hey guys, today we'll be going over chapter 9. So this chapter covers data reexpression. In the last two chapters, we were going over scatterplots, right? And then in all of our scatterplots, we basically wanted a straight distribution. So chapter 9 covers what we do when our data isn't straight. When our data isn't straight and we see some kind of curve like this, what we want to do is we want to take this curve and make it into something straight. So that is one of the main goals of data reexpression, which is number 3 over here. The other 3 goals are 1, to make distributions more symmetric. So if you have a very heavily skewed distribution, you can make it more symmetric through data reexpression. The second goal is to make the spread of the data set more similar. So this is saying if you have a bunch of box plots lined up together, but then they're very different in terms of where they lie, you can re-express the data to make them closer to each other. So you bring them all closer to a certain value. And the fourth goal would be to make a scatterplot have more uniform distribution and eliminate clusters. So if you have a very obviously clustered scatterplot, for example, a big cluster here and then a more even distribution out here, then you could re-express it to look something more like this. So a more even overall distribution. These are the main ways that you can re-express your data. The most common type of data re-expression is taking the logarithm of either your x variable or your y variable. This process relies heavily on trial and error, so a lot of the times you'll just put your data into the calculator and then keep making scatter plots until something looks somewhat like a line. I will go over this in a separate calculator video, but over here is the times when you would use each data re-expression. Whenever you have some kind of light bend, then you would take the logarithm. So you square your data when you have a severely left skewed unimodal distribution, so that would look something like this. If your histogram had a massive tail on this side and then went outwards this way with a big skew, then you could square the data to make it look more similar. Our 1 on our ladder of powers is keeping the raw data, so that is when our data already looks straight. We're not doing any further transformations to it. The power of 1/2, so that is when we take the square root of the data, is used on counted data. So our logs is used when we have some slight bend in the data, and then taking the negative reciprocal square root of the data is a more uncommon one. However, if you feel that log is not enough to make your data straight, then you can try this one. And then finally, taking the negative reciprocal of your data is used the most for when you have ratios. So this ladder of powers, you would normally start from your power of 2. So start by trying to square the data, and you work your way down the ladder of powers until something looks about straight. In these cases, your 2, so your power of 2 is your most gentle transformation, and as you go down further down the ladder of powers, your changes get more and more drastic, so you need to find the one that brings you the closest to a straight line. If you go too far, then you might end up going from a scatterplot that looks like this to a scatterplot that looks like this, and you don't want that. You want to have something in the middle with a good line shape. So logs are used so much that we actually have a separate table for them. First, we have our exponential model. This is used the most when our data is increasing by percentages. And this is when we take the log of our y-axis. So our y hat gets the log. Our x does not change. So our equation would look like this. Log of y hat is equal to a plus bx. Now for our second one, we're taking the log of x instead. This one is actually used quite a lot, and your equation would look like this. So we leave our y hat as is, and instead we take the log of x. And then finally, we have our Goldilocks model. So this is when we take the log of both x and y. So if we wrote that out in an equation, it would look like this. So a plus b log x. We use this one when we're going down our ladder of powers up here, and then we find that one transformation is not enough, but the other one is too extreme. So if we were in between 2 steps of the ladder and one step of the ladder looked like this and the other step of the ladder looked like this, then we could try the Goldilocks model to see if that would give us a more gentle transformation than the step between these 2 initial things. So when you actually have to transform the data, it actually takes a while and it is not too heavily covered in most statistics courses. Some more common questions you would see would look like this. So they would give you an already transformed equation or data set. You would have to solve for certain values. So take this one for example. This one is actually a Goldilocks model. So we took the log of both the y hat and the x. And then the question asks you to solve for x when your y hat is equal to 52. So this one is just going back to algebra 2, I'd say. Algebra 2 or pre-calculus. And you would just plug in your 52 for y hat. So log of 52 is equal to 3 plus 2.3 times log x. And x is the one that we're solving for. So for those of you that need to touch up a bit on your logarithms, you'll see that there is no base for our log here right now. So that means we have an invisible base 10 here. So keeping that in mind, let's solve this. So the first thing we need to do is get it to where only our log x is left on one side. So let's move everything to the left side with the log 52. So first let's subtract 3 on both sides to get rid of this term. Minus 3 is equal to 2.3 times log x. Now we need to bring our 2.3 over as well. So if we plug that into the calculator, we get that is negative 0.558 is equal to log x. So what we did was we plugged this into the calculator and divided by 2.3. And now we do a little bit of a rotation to get rid of our log and solve for x. So since we don't see anything down here, we can just put an invisible base 10 here. And now we bring x down, and then negative 0.558 goes into an exponent. So x is equal to 10 to the power of negative 0.558, which is equal to 0.2765. So now we know that when y hat is equal to 52, our x is equal to 0.2765. So a lot of calculators have the function where when you take a scatter plot, you can actually make an exponential or nonlinear model fit your scatter plot. So you would have a line of best fit that is curved instead of the lines that we're usually using. The reason why we're not using them here, even though it is convenient, is that this is actually just a linear statistics course. If you're taking a more advanced statistics course, you will get into it. But here we're just going to be dealing with our linear models. So that is actually it for chapter 9. Thank you so much for watching. I hope you learned something. Peace.